Welcome to True Projects. In this video, we are going to explain about the project entitled as a machine learning based real-time remaining useful life estimation and fair price strategy for electric vehicle battery swapping stations. So before getting into the video, let me give you the brief explanation about the project. Today, electric vehicles are becoming one of the most important solutions to reduce environmental pollution and dependency on fossil fuels. But despite their advantages, one major change still remains: long battery charging times. This issue often discourages users and slow down the global shift towards electric mobility. To overcome this, battery swapping stations have emerged as a fast and convenient alternative. Instead of waiting for hours to charge, drivers can replace their depleted battery with a fully charged one in just a few minutes. However, this system introduced a new problem: fairness in battery exchange. Coming to the abstract states that the rapid growth of electric vehicles has made battery swapping stations an essential solution to avoid long charging times. But these stations face a major issue: unfair pricing caused by difference in battery health. Users may return a battery with a long remaining useful life and receive a degraded one without knowing, leading to dissatisfaction and loss of trust. Our project solves this problem using a machine learning model that predicts the RUL of each battery in real time. After comparing several algorithms, XGBoost proved to be the most accurate and efficient for real world use. With this information, a dynamic pricing system is applied, calculating cost based on RUL differences and key performance indicators, ensuring that every swap is fair and transparent. This approach improves users' confidence, enhances operational efficiency, and supports the development of a more sustainable and reliable EV battery swapping ecosystem. Coming to the existing system states that current battery swapping stations mostly use fixed pricing or subscription models that do not consider the actual health or remaining life of the batteries being exchanged. Because of this, users may return a healthy battery and receive a degraded one while still paying the same price, leading to unfair and inefficient swaps. Although some studies focus on improving battery allocation, charging strategies, or overall station optimization, very few considered fairness based on remaining useful life. Existing machine learning methods for predicting battery health also struggles with high computational demands, making them unsuitable for real-time use. As a result, today's system lack transparency, fairness, and the ability to accurately reflect battery values, ultimately causing user dissatisfaction and operational changes. Coming to the proposed system or base paper work. The proposed system works through two major components: real-time RUL estimation and dynamic fair pricing. First, it uses the XGBoost regression model to accurately predict the remaining useful life of both the user's battery and the station's battery. XGBoost is chosen because it handles complex battery behavior, provides high accuracy, and works efficiently with low computational time, making it suitable for real-time applications. Once the RUL values are determined, the system applies a fair price mechanism that adjusts the swap cost based on difference between the two RUL values. Additionally, battery performance factors such as discharge time, charge duration, and voltage characteristics are also included, each weighted by how strongly they related to battery health. If the station provides a better battery, the user pays a small difference. If the user returns a better battery, the station compensates them. The system also ensures quality control by rejecting batteries below a minimum RUL threshold. Overall, this approach creates a transparent, data driven, and fair battery swapping process. Coming to the dataset, the dataset used in this study is a publicly available in Kaggle. The dataset titled as Battery Remaining Useful Life (RUL), containing detailed performance measurements of 14 18650 lithium ion batteries with NMC/LCO chemistry. Each battery has a nominal capacity of 2.8 Ah and was tested for up to 1000 charge discharge cycles at a constant temperature of 25 degrees using a CC-CV charging method at a C by 2 rate and discharging at a 1.5 C rate. The dataset records several key attributes during each cycle, such as discharge time, which indicates how long the battery can deliver current, time 4.15 volts, representing the duration required for the battery to reach 4.15 volts duration charge, and constant current duration, which reflects how long the battery remains in the CC charging region. An early indicator of degradation. Additionally, attributes include 3.6 V and 3.4 V voltage decrement time, which helps identifying mid-cycle degradation. Maximum discharge voltage, a strong indicator of battery performance and internal health. Minimum charge voltage, which signals deeper levels of aging. And total charging time, which typically increases a degradation progression. Collectively, these attributes offer a comprehensive representation of each battery's aging behavior, making the dataset high, suitable for training machine learning models for accurate RUL prediction, though it may be limited by its controlled testing environment and lack of diverse real-world conditions. Coming to the novelty or extension or enhancement or improvement. As an extension, we implemented advanced ensemble models such as the stacking regressor, which achieved the lowest RMSE of 3.039, and the voting regressor, which recorded the second lowest RMSE of 3.329, outperforming all other models. We also developed all the existing and proposed regression models for comprehensive comparison. To enhance the model transparency, we applied explainable AI techniques like LINE and SHAP to explain feature importance and how each input contributes to the predictions. Additionally, a user-friendly web interface was created using the Flask framework, enabling users to input battery features and obtain RUL predictions using the trained machine learning models. Coming to the flow of the work, first we need to import the packages. Required Python libraries like NumPy, Pandas, Matplotlib, Scikit-learn and XGBoost are imported to handle the data pre-processing, visualization and model building. Next, exploring the dataset. The battery RUL dataset is loaded and examined to understand its structure, feature, number of records and overall behavior. Next, we have data pre-processing. The dataset is cleaned by removing duplicate rows and preparing the data for accurate machine learning training. Next, data visualization. RUL distribution is plotted to see lifespan patterns and a correlation matrix is created to understand relationship between features and RUL. Dataset splitting. The dataset is divided into 80% training data and 20% testing data to evaluate model performance or unseen samples. Next, building the regression models. Multiple regression models including random forest, lasso, gradient boost, kernel ridge, decision tree and XGBoost are created. Ensemble models like voting and stacking are also built to improve the accuracy. Next, training the models. Each model is trained on the training data set to learn the relationship between the battery features and RUL. Next, we compare the models with metrics. All the models are evaluated using MSE, RMSE, MAE, R-square, score, and SSE to identify the most accurate model. Next, we have comparison of the graphs. Graphs are plotted to visualize, compare model performance across evaluation metrics. Then, we need to save the best model. The best performing model, usually XGBoost, is saved for future predictions without retraining. Next, we applied explainable AI visualizations. Explainable AI tools are used to show which feature influence the model's prediction, improving the transparency and trust. Coming to the front end, a Flask is used to create a simple UI with authentication supported by SQLite. User enter battery feature values into the front end for prediction. The system pre-processes the input and uses the safe model to predict the battery RUL. The predicted RUL is shown to the user in the front end screen. The algorithms used in the project are random forest, lasso, gradient boost, kernel ridge, decision tree, and XGBoost. As an extension, we applied OT and stacking regressions. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements: operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to the front-end logic. It could include code written in Python that handles server-side operations such as processing users' requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of codes, graph, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store user information. Now, coming to the execution of the project, first, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. By using the command cd and space, we need to paste the path, then click on enter. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Get Started button. Now, click on Get Started button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a password. Then click on Create an account so that all the given details are stored in signup.db and the login HTML will be opened, where we need to access the application by username and password. Then click on Sign in. The prediction page has been displayed. In this, we have Home button, Prediction button, Graphs button, Notebook button, and Sign out button. So this is a home page. And firstly, we need to click on Prediction button. Then the battery remaining useful life fair price prediction form will be opened, where you need to enter the battery performance parameters to get real-time RUL estimation and fair price using our advanced ML algorithms will be predicted through the output. So firstly, the cycle index is 8. The discharge time is 5955.3 and the decrement 3.6 3.4 volts is maximum voltage discharge will be 4.013. Minimum voltage charge will be 3.501. Time will be 5017.495 and the time constant current will be 5967.55 and the charging time will be 5967.55. So now click on predict RUL and price so that the given inputs are processed and the output will be displayed as the remaining useful life will be 1105.3% and the fair price is of $4.7. And here we also have the battery health analysis, like the given output is based on the temperature status, voltage sustainability, model performance, cycle efficiency, charging time, and the features used. And we also have some recommendations like optimal use, like continuous charging usage patterns for maximum battery life, temperature monitoring, like monitor battery temperature during the high load operations, charging schedule, maintain regular charging cycles for optimal performance, and pricing logics will be like your battery exceeded our base standard, so you receive the calculation of fair prices. And we also have the additional information like ML model has been used, analyzing time, data points analyzed, and prediction date. Here we have two buttons like new prediction and view analytics. If you click on new prediction, again the form will be open where you can give your inputs to predict your output. Now click on view analytics. When you click on view analytics, so that all the graphical representations in the ML model performance metric graphs will be displayed. First, we have distribution analysis of battery remaining useful life predictions. So let me open the graph. This histogram shows how the remaining useful life RUL values are distributed in the dataset. The RUL values span from near 0 up to around 1100 cycles. The distribution is fairly uniform, meaning all RUL values appear with similar frequency. The overlaid KED curve illustrations the density of data points, indicating no major skewing or clustering. A uniformly distributed RUL helps ensure that models train efficiently across the entire lifespan of the battery rather than being based towards early or late cycle data. And next, we have feature correlation analysis for battery performance parameters. This heat map visualizes the correlation between different battery related features such as discharge time, voltage measurements, charging time, and the cycle index. Strong positive correlations are shown in warm colors like red or orange, while strong negative correlations appear in cool colors like blue and purple. For example, discharge time, time constant current, and charging time shows very high positive correlations with each other, meaning they tend to increase together. Meanwhile, cycle index is strongly negative correlated with maximum voltage discharge, showing that voltage tends to decrease as the number of cycle increases. This matrix helps identify which feature may be most important when predicting battery aging. And next we have mean squared error analysis for model performance evaluation. This bar plot displays the mean squared errors for the models. MSE is simply the square of RMSE and exaggerates large errors even more. As expected, extinction stacking, extinction OT, and XGBoost shows the lowest MSE values, confirming they are the most reliable. The kernel ridge model again shows an extremely high MSE, making it clear that it struggles significantly with the dataset. The model ranking is consistently across MAE, RMSE, and MSE. And next we have root mean square error visualizations for model accuracy assessment. The chart compares the root mean squared error between the same set of models. RMSE penalizes large prediction errors more strongly than MAE. Again, extinction stacking has the lowest RMSE followed closely by extinction OT and XGBoost. showing these models handle large deviations well. Kernel Ridge has a significantly higher RMSE than all models, reinforcing that it performs poorly. The consistent trends across MAE and RMSE indicates that ensemble methods give the best prediction stability. Next, we have mean absolute error analysis for prediction accuracy evaluation. This bar plot compares the mean absolute error of several machine learning models used for predicting battery remaining useful life. Low MAE indicates better predictive performance. From the plot, extinction stacking and extinction voting achieve the lowest errors, meaning they produce the more accurate predictions. Random forest, decision tree, and XGBoost also perform well. In contrast, the kernel ridge model shows the highest MAE, indicating poor accuracy compared to others. Next, we have sum of squared errors analysis for model performance assessment. This graph compares the sum of squared errors for various machine learning models. SSC measures how far the model predicts deviated from the actual values. The lower the SSC, the better the model fits the data. In the chart, most models shows relatively low SSC values, but the kernel ridge model stands out with a very high SSC, indicating poor performance for this dataset. Models like Random Forest, Lasso, XGBoost, and the other two extinction models exhibit much lower SSC, meaning their predictions are much closer to the true target values. The voting and stacking extinction seems to perform especially well, showing some of the smallest SSC values among all models. Next, we have SHAP values for explainable AI and feature important analysis. This SHAP summary plot shows how each feature influences the model's predictions and ranks them by importance. The feature cycle index is the most influential, indicating that as the battery progresses through more cycles, the model predicts lower output values, which typically reflects battery aging, discharge time, and maximum voltage during discharge. Also important. Higher discharge time and higher discharge voltage generally increases the model's predictive values, suggesting that battery performing well during discharge appear healthier to the model. In contrast, features related to charging such as charging time and time at 4.15 volts shows that higher values tends to decrease the prediction, indicating that spending more time in high voltage or long charging phase may signal degradation. Minimum voltage during charges shows the opposite trend. Higher minimum charge voltages pushes the model output upward, reflecting better battery condition. Meanwhile, features like decrement 3.6 to 3.4 voltage and time constant current have smaller overall impact but still shows pattern where higher values tends to lower the predicted output. Overall, the plot highlights how both aging related indicators and performance related indicators shape the model's assessment of battery health or capacity. Now, click on sign out. So finally, the project demonstrates that a machine learning based approach can accurately estimate the real-time remaining useful life of electric vehicle batteries, enabling smarter and more efficient operation of battery swapping stations. By integrating RUL predictions with a fair and dynamic pricing strategy, the system ensures that users are charged appropriately based on the true condition and expected lifespan of the batteries they receive. This not only increases transparency and trust, but also helps station operators optimize battery usage, reduce premature degradation, and improve overall economic performance. The combination framework ultimately supports a more sustainable, data-driven, and user-equivalent battery swapping ecosystem. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.